Howdy, and welcome back to the Aviation Weather Series. This is part 2, where we're going to be talking about heat and temperature. If you haven't seen the first video in the Weather Aviation Series, go back and watch that one. But here we are. So I'm Dr. Andy Molter. I'm a CFI, CFII, MEI. I'm a former corporate pilot, and I'm a professor of aviation. So in this series, I'm talking about aviation weather. These are the same lectures that I give in my college classes. So I'm glad you're here so that you can learn about aviation weather. So in this video, we're going to discuss the difference between energy, heat, and temperature. We're going to talk about the different scales used to measure temperature, the different types of heat transfer, which are radiation, convection, and conduction. We're going to talk about measuring the temperature in the atmosphere, and we'll be talking about isothermal layers and temperature inversions. So, hey, you know what? Aviation weather is not the sexiest topic out there, but I'm going to do my best. All right, so heat and temperature. So there's a few terms you need to know and a couple of facts. So just a quick little fact, air temperature varies from one location to the other. And there are so many factors. And just a quick note on weather in general. You know, we're never going to completely understand weather. Even meteorologists at the Aviation Weather Center have told me that, you know, it's an art to be able to forecast the weather, you know, and so there's a science to it, but still, it's very hard to actually know what the weather's going to do, and so it's more just trying to have the best education in weather. So that's why I'm making these videos, so you can be the most educated in weather. All right, so matter. Matter is a substance of which all physical objects are composed. So, you know, you're made of matter, I'm made of matter. So matter consists of atoms and molecules which occupy space and, very importantly, have mass. And so mass is not weight. Weight is caused by gravity. So when gravity pulls on a mass, that gives it weight. All right, so now we have energy. So energy is the ability to do work. It exists in many forms, and it can be converted from one form to another. And there's two types, potential and kinetic. And so I like to think of, let's say you're standing on top of a building and you hold a bowling ball off the edge of the building. Well, when you're holding it, that's potential energy. But when you release it, now it's kinetic energy. And because of gravity, you know, it accelerates at 9.8 meters per second squared. And so the more it speeds up, the more kinetic energy it has. And then we have heat. So heat is the total kinetic energy of the atoms and the molecules composing of that substance. Atoms and molecules in a substance do not all move at the same velocity, and so therefore we're going to have different amounts of heat. You know, another way to look at this is to consider that heat is an exchange of energy. So here we have two different molecules, and when you have molecules in a volume of space, they're moving around. And as they move around, they make contact with the other molecules and they exchange electrons, as shown here in the center of the picture. And so this exchanging of the electrons is the energy, that is heat. And so the more exchanging of energy we have, the more heat there is. And so the more kinetic energy, that means molecules are moving faster. That means they're going to be exchanging heat more often, and therefore we have more heat. And then we have temperature. So temperature, this is an arbitrary term. So it's an assigned numerical value that represents the average kinetic energy of the atoms and molecules within matter. And so the higher the average kinetic energy will produce a higher amount of heat. So therefore we assign it a higher temperature. We use Celsius, Fahrenheit, Kelvin, and those are just arbitrary, units of measurement that we came up with. If I wanted to come up with this Moltar Aviation, let's just call it units of Moltar. So if I said, hey, that object over there has a temperature of 1,000 moltars, What does it mean? Well, we have to assign meaning to it. And we could say 1,000 moltars. Oh, that water is 1,000 moltars. That's freezing. But then, 10 million moltars could be boiling water. So it doesn't matter what the numbers are until you assign it based on a scale. And so the way that we measure temperature is with a thermometer. Now, the first one we want to talk about is Kelvin. So when we talk about temperature in Kelvin, Kelvin is just a unit of measurement used by scientists. And there's the bottom of the scale of Kelvin starts at 0. And so 0, and we don't say 0 degrees Kelvin, it's just 0 Kelvin. 0 Kelvin is absolute zero. And that means that is the theoretical absence of all thermal energy. So there's just no energy. So therefore, there must be no mass. I know scientists are trying to create a space in which there's absolute zero temperature, but they haven't been able to do it yet. Maybe one day they will, but I don't know. But to do so, you have to have absolutely no energy to have absolute zero. All right, then we have Celsius. So Celsius is the most commonly used temperature scale in the world from countries that haven't landed on the moon. But then the FAA back in the 90s, they went ahead and adopted the ICAO's unit of measurement for temperature, which of course is Celsius. So unfortunately, here in America, we are using Celsius for temperature, but everything else is the imperial system. So in Celsius, the freezing point of water is 0 degrees Celsius. Boiling point of water is 100 degrees Celsius, and this is under International Standard Atmospheric Conditions. So if you saw the first video, we know that International Standard Atmospheric Conditions is when it's 15 degrees Celsius, 290.902 inches of mercury, and where is that? Do you remember? It's at sea level. So that's a very important component of International Standard Atmosphere, is it's at sea level for 15 degrees Celsius and 290.902 inches of mercury. All right, and the Celsius scale and the Kelvin scale, the increments in degrees is the same. So if we increase the temperature by 10 Kelvin, then the increase in Celsius would be an increase in 10 degrees of Celsius. All right, then of course, as Americans, we know, here in America, we got Fahrenheit. So Fahrenheit is the most common temperature used in the United States, except for aviation purposes. So us pilots here in America, I don't know anybody that's fluent in Celsius. So we always have to think in terms of, okay, what do we know in Celsius versus for Fahrenheit? All right, so freezing point of water is 32 degrees Fahrenheit. The boiling point of water is 212 degrees Fahrenheit. And remember, that's under International Standard Atmospheric Conditions. So that's 290.92 inches of mercury and 15 degrees Celsius at sea level. All right, so the Celsius scale and the Kelvin scale, remember, the increments are the same, but not for Fahrenheit. And then here's just a little comparison. So here on the left, we have Kelvin. So 288 Kelvin is equal to 15 degrees Celsius, which is equal to 59 degrees Fahrenheit. Do you need to know that? Not really, but just want to show it here for your knowledge. Okay, so remember, heat transfer is energy transfer as a consequence of temperature difference, the exchange of energy, kind of like what I showed you with the molecules. And so when a physical body has a higher thermal energy than another physical body, a transfer of thermal energy occurs until a thermal equilibrium occurs. So, if you're married, you know it. Your spouse is super cold. You're nice and toasty. So they take their cold feet and put it on your body, and now what you're doing is you're exchanging your heat for their cold. And so, you're losing heat, but they're gaining heat. Now, I know I just said the word cold. Cold is an arbitrary term. Hot is an arbitrary term. So they don't mean anything unless you add context to it. So heat. So you give your spouse, your cooler spouse, heat, and that cooler spouse takes heat from you. And so heat transfer can never be stopped, but only slowed down. All right, and so there's three types of heat transfer. So there's radiation, conduction, and convection. So here we have a picture of a dog sitting in front of a fireplace, and the fire is not on the dog. It's just nearby, and so it's electromagnetic radiation from the fire that's going out from the fire, and whatever makes that radiation makes contact with is transferring that heat. All right, and so we experience this daily. We receive solar radiation during the day, and then at night, the Earth radiates the heat out. And so, and this is a perfect balance. If it wasn't perfectly balanced, if we received more heat than we expelled, well, then we would burn to death. Or if we expelled more heat than we received, well, then we would freeze to death. Okay, another, when we're talking about solar radiation, it really matters on the season, the time of day, and when we enter latitude as to how much heat we have as a result of the solar radiation. So on this picture on the left here, and the picture on the right, we have what's called the solar zenith angle. And the solar zenith angle is the angle at which we're receiving solar radiation. So here on the left, we'll say we're at, so it says 0 degrees, so we're at the equator. And at the equator, at the, the summer solstice and, at the Tropic of Cancer, where it's a direct 0 degree difference. It's a perpendicular solar zenith angle. And so it's directly receiving sunlight from the sun. But you go much further north, like say 50 degrees north latitude, then the ground is receiving that sunlight at an angle. And so the same amount of radiation is being transmitted, but the amount of radiation received is a lot more focused, and it's in a smaller region at the equator than it is at 50 degrees north latitude. So this Y, we'll say that this is like 500 yards for this amount of energy received, whereas this was on the right 500 yards. On the left here, this would be, let's say, 50 yards. And so we're getting a lot more solar radiation, so it's going to be hotter at this location on the left than it is on the right. And then, of course, when the sun sets, this diurnal cycle, when the sun sets, then we have no solar zenith angle, so we're not receiving any solar radiation. We're just expelling radiation, terrestrial radiation. All right, next we have conduction. So conduction is when heat is transferred from an object making contact with another object. And so an example of this is a pot on the stove. The pot has water in it, and that coil is heating the pan, which is conducting heat. Now this kid here, the phrase, you F around, you find out. Well, this kid messed around, he found out. So when that hot water makes contact with his skin, he's going to find out how conduction works. It's going to burn his hand. That the conduction of his hand is going to receive heat because of the contact with the water. So air is a very poor thermal conductor, and it really depends on the material as to how conductive it is. So silver is the most, in this table here, is the most conductive, whereas steam is the least conductive. So here at the top, so silver, let's say you had a silver wand and you stuck it in a fire. So in that sense, because the silver wand is in the fire, that would be conduction. Since you're touching that metal wand, that silver wand, you would feel that heat very quickly. But if we go down lower, air next to steam at the bottom of this list is a very poor conductor of heat. So, if there's like let's say you have a boiling pot of water, well, you could stand right next to it because that pot of water that's boiling, uh, you're not making contact with that pot of boiling water if you're standing right next to it because there's that cushion of air in between you and the water. So, and air is a very poor conductor of heat. So, you don't feel that heat. Now, you might feel the radiation of the heat, but not the actual, but not from conduction. Okay, so next we have convection. So, convection is the transport of heat within a fluid, such as air or water, via motions of the fluid itself. Because remember, when you have molecules that are moving, the faster it moves, the higher the kinetic energy, the more heat there is. So, here in this picture, the radiation. Well, in this picture, the radiation is because the pot is above the coil, the heating coil. But if the pot was on the coil, that'd be conduction. But the water that's in contact with the pan in this picture, that is conduction. And then the water itself is hot. And so if you put like an egg inside there, it's the water that's heating the egg through convection because the water is moving really fast around the egg. And that fast moving water is creating more kinetic energy, which is then going to heat up the egg. And so another good example of this is an air fryer. So if you have an air fryer, if you don't have an air fryer, we highly recommend you get one. They're amazing. They make vegetables taste amazing. But an air fryer, it's not a fryer. What it is, it's actually a convection oven. It's a tabletop convection oven is what an air fryer is. Okay, then we have, so thermal response is just the temperature response to the input or output of some specified quantity of heat. And then the next term I want you to know is specific heat capacity, also known as specific heat. And so the specific heat capacity is how much heat can something receive before it changes temperature. So the thermal response is the response measured in specific heat capacity. And so let's look at this table here on the left and this picture on the right. So water has a very high specific heat capacity versus sand or lead that has a very low specific heat capacity. So what does that mean? So when we look at this picture here on the right, the left and the right of this right picture, on the left side of this picture, we see candles on both sides. It says 4.18 joules of heat energy. We don't care about joules because remember, we're pilots. We're not scientists. But what you want to understand is, hey, candles got fire hot. So the fire is heating up a cylinder of water, and you got another candle that's heating up a cylinder of sand. Well, remember, when we look at this table on the left, water has a very high specific heat capacity. And so over the same amount of time that we receive that heat from the candle, when we look to the right, the water only increased in temperature 1 degree Celsius. But over that same amount of time, that sand that received that heat rose to 30 degrees Celsius from 25. So, so if you think about it, if you ever go to the lake or to an ocean, it could be really hot outside. You step on the sand, your feet are burning if you're walking barefoot because that sand's really hot. It's because it's receiving that solar radiation. But then when you hop in the water, it's nice and cool. It's not too hot because even though it's receiving all that same amount of solar radiation, it doesn't heat up that fast because it has a very high specific heat capacity. And so whenever you have bodies of water around land, then that land surrounded by water, the annual temperature variation is not going to be that much compared to places, inland. So here's an example. So San Francisco, it's right on the ocean. It's surrounded by water. And so the annual change in temperature isn't that much. So in winter, we see here that the temperature is around, 10 degrees Celsius. But then in the summer, it's up to like 20 degrees Celsius. So it's really not that big of a change. But then, here, in Kansas City, oh man, it gets as low as like almost -3 degrees Celsius, but as high as 30 degrees Celsius. So it's a big temperature change. And if you don't know where Kansas City is at, it's west of St. Louis. It's in Missouri, on the border of Kansas, and there's a Kansas City, Kansas. But it's right in the center of the country, surrounded by land, no bodies of water for 1,000 miles. All right, and then we also have temperature variations with altitude. So if you remember my last video talking about the atmosphere, if you haven't seen it, go back and watch it. And don't forget to subscribe, because that way you can see all the videos in this weather aviation series. So as we go up in altitude, the standard lapse rate is 2 degrees Celsius per 1,000 feet. Now, this seldom exists, but don't worry, we're going to talk about the lapse rate in a lot more detail. And I know that it might get scary, but I can explain it really well, and you'll get a really good sense of what it all means. So the standard lapse rate, 2 degrees Celsius per 1,000 feet. And the way that, the rate at which the temperature decreases is a good measure of the stability of the air. And so the way that we measure this is by doing atmospheric sounding that we do with a weather balloon. So the National Weather Service, they have a whole bunch of meteorologists all around the country that release these weather balloons twice a day, every single day, one in the morning, one in the evening, and they do these atmospheric soundings. So included in those soundings is, measuring the temperature, the dew point, and the wind. All right. And so typically, like we said, the standard lapse rate is 2 degrees Celsius per 1,000 feet, but sometimes we'll have an isothermal layer, which is a layer within the atmosphere where the temperature remains constant with height. So in this picture here, we see that the temperature is decreasing with the increase in altitude, but then here at, I guess, about 14,000 feet, it just kind of stays the same for a couple or a few thousand feet, but then it starts decreasing again. So that would be an isothermal layer. The faster that the temperature decreases, then the less stable the air is. The slower the air decreases, the slower the air temperature decreases with an increase in altitude, the more stable it is. And if it doesn't decrease, or actually the temperature actually increases, then the air is very stable. And so when the temperature increases with altitude, that's what we would call a temperature inversion. And that's where, and so we have two types. We have a surface-based inversion and a temperature inversion aloft. And so if we have a surface-based inversion, that's probably going to happen when the sun sets, and then the ground has a low specific heat capacity, so it's going to let a lot of its heat away right away. And so the surface cools down a lot, and then the air above is now warmer. And so there we have a surface-based temperature inversion. And then when we have temperature inversions aloft, so like when we go from the troposphere to the stratosphere, then we have another temperature inversion aloft. And the flying weather in temperature inversions generally very stable, very smooth, and calm. So it's nice flying weather. Now, you might have poor visibility, but other than visibility, it's nice flying weather. And so here in this picture, we have a surface-based temperature inversion where the temperature increases in altitude, but then at a certain point it starts decreasing in altitude again until it starts increasing in altitude again and then decreasing. All right, so a little review. So what's the difference between energy, heat, and temperature? So remember, energy, every object has energy. The more kinetic energy, the more heat there is. And then temperature is just a measurement, an arbitrary measurement of that heat. How is heat transferred through radiation? Do you remember? Well, it was conduction, convection, and radiation. All right. And for the rest of these, can you answer them? If not, you can go ahead and pause here and think about it. But if you can, go back in the video and watch it a little bit. Otherwise, stay tuned, subscribe, please like, and if you have any questions, please comment in the comment section below, and I'll be happy to answer them in another video, or I'll just straight up respond in the comment section myself. So thanks for watching. You take care.